Okay, so now we are going to learn another concept called thermal conductivity. Okay, so now let us take one defined volume of a conductor. So say this is the cross section, and from one end to this end is slightly higher temperature T, and this end slight lower temperature with a gradient with a temperature difference of say dt, that is a small temperature difference. Okay, and this distance from one end of the conductor to another end, it is lambda. Okay, so now from the kinetic energy, that is the gas theory, because electron here it is assumed as it is moving inside the conductor as a gas molecule. So that at end A, the energy, say this is the end A and this is the end B. Okay, so already we learned it. So the energy, the energy per unit volume at end A, that is 3/2 K, small k, into the absolute temperature. Okay, and the energy at the end B, that is 3/2 K T minus dt. Okay, so now the difference of energy in unit volume, if we find, because that energy difference, it will cause the movement of the electron. Okay, so that means you have to minus this quantity from this quantity. So if you minus, then you see this kt, it will be cancelled and this minus will become plus, so it will be, that means what I am telling, this 3/2, the resultant energy which will cause the movement of the electron from the hotter end A to the colder end B, that will be 3/2 kT minus 3/2 K T minus dt. Okay, so simply this if you do, it will come 3/2 K dt. This is small k dt. Okay, now this energy is per unit volume, and once we are talking about the conductivity, it will come as a cross section. So volume means, if you want to convert the unit volume to unit, because unit volume, if you call the unit volume, it is m to the power, the dimension is m to the power minus 3, and unit cross section means m to the power minus 2. So we want to find out the energy, the net energy at hotter end per unit cross section per unit time. Okay, but this unit is dimension is unit volume, that means m to the power minus 3. Okay, so what is to be done now? So the energy, this energy, say the EA, this energy is, now we want the energy per unit cross section per unit time. But what we calculated this one, this is for average energy for unit volume for a single electron. So now we have to multiply the number of electron. Okay. Now here one thing, the electron can move any direction. It can go x direction, y direction and z direction. So normally the number of, if the n total number of electron is 3, so for each axis it may travel n by 3 number of electrons. Now this n by 3 number of electrons can go towards positive direction, positive x-axis or negative x-axis. Again it will be divided by 2. So this is for a particular axis, it will be n by 6. Okay. Then per unit time, that means you have to multiply by the velocity of the electron which is moving. Okay, because what I told, this should be that this energy is per cross section, means per meter square per second. So this V dimension is, velocity dimension is meter per second. So if it is multiplied by meter per second, so what will happen, this m cube and m, it will be m square and second to the power minus 1. So to make the things dimensionally correct, I am multiplying the number of electron into the velocity. So now this 3 it will be get cancelled. So final expression we will get 1 by 4 k dt n into V. Okay. So this is for the hotter end. Now the classical theory of the electron, it told that the electron can move from any direction. Anyway, the energy of hotter end, that means end A, it will be slightly higher, but the electron will move also from, collide also from B to A, that is also possible, but here energy is less. So in that aspect, if you write the same equation in opposite way, so the energy of the electrons that is moving from B end to A per cross section per unit time is minus 1 by 4. Simple or minus sign it will come. So that is minus 4 k dt into n into V. Okay. Now if we find out the resultant energy, that is the energy EA minus EB. Okay, so EA is equal to 1 by 4 k dt nV and EB is equal to minus 1 by 4 k dt nV. So if you do that, if you do the resultant energy and if you minus EA, if you do EA minus EB, so this minus will become plus, so 1 by 4 plus 1 by 4, it will be half, k small k dt n into V. Okay, so this is the total resultant energy. Got it? Now this energy, it is the thermal energy. It is the thermal energy. So that thermal energy can be written because it is happening to thermal conduction. So now if you write the thermal law, Fourier's law of thermal conduction, that we know it is Ka, that is the cross section, dt by dx. Okay. Anyway, this A is 1 because unit cross section both side. So now this half K, this K is capital K. It is thermal conductivity, and this K is small k, which is the Boltzmann constant. So now we can tell half small k dt nv is equal to K, capital K, dt by dx. Now this dt is cancelled. Now the thermal conductivity K, it becomes as half small k n v into dx. This dx, the distance, I can tell it is as lambda. For this particular explanation, I assumed it as lambda. Okay. Now if we replace that equation in terms of relaxation time, already to establish the electrical conductivity we understood what is called the relaxation time. Okay, so the relaxation time means the time taken to travel the mean free path by the electron. Okay, so that distance is equal to the velocity into the relaxation time. So now if I replace this value here, so the thermal conductivity, that means capital K, it will appear as half K, here we will put V tau, so that means V square K tau, sorry, V square tau. So this quantity, it will appear here. I am putting in place of lambda, I am putting V tau. So what will come? Half, then the total number of electron, then this V and this V, it will be V square. Okay, then the Boltzmann constant K into tau. So this is the final equation of thermal conductivity in terms of relaxation time, and this is the expression, for thermal conductivity in terms of the mean path and the velocity of the electron. Okay, so this is the final expression of thermal conductivity of a conductor. So this K is a capital K, which is representing the thermal conductivity, and this K is a small k, which is Boltzmann constant. So hope you understood the concept. Thank you so much.